Hello all, I am Saraswati working as Associate Professor, Department of ECE, K.S. Rangasamy College of Technology. Course name is Control Systems Engineering. Today we are going to discuss about mechanical rotational systems. Now what is mechanical rotational systems? Mechanical rotational system means moving with respect to fixed axis. It consists of three basic elements. First one is moment of inertia, second torsional spring, third dashpot. Now what is moment of inertia? So that is the weight of the mechanical rotation system is represented by the moment of inertia of the mass. The moment of inertia of the system is considered as center of the gravity of the body. And second, torsional spring means the elastic deformation of the body. And third, dashpot is friction existing in mechanical rotational system. The dashpot is a piston rotating inside a cylinder filled with viscous fluid. When a torque is applied to a mechanical rotational system, then it is opposed by opposing torques due to the moment of inertia, friction and torsional spring of the system. So therefore the applied torque and the opposing torques are in opposite directions. So by the Newton's law of motion, the algebraic sum of torques acting on the system is 0. And the Newton's law states that the sum of applied torque is equal to the sum of opposing torques on a body. Let us now see the torques opposed by these three basic elements. Now we derive the torque balance equation of ideal three basic element. A moment of inertia in mechanical translational system, the mass stores kinetic energy. Similarly, in mechanical rotation system, moment of inertia stores kinetic energy. Now consider the ideal mass element which has negligible friction and elasticity. The opposing torque is due to moment of inertia is proportional to the angular acceleration. So now when where T is the applied torque and Tj is the opposing torque due to moment of inertia of the body. So the opposing torque is given by Tj is proportional to angular acceleration alpha. So Tj is equal to J alpha is equal to J d square theta by dt square. By Newton's law, the sum of applied torque is equal to sum of opposing torque. So now the T is equal to Tj is equal to J d square theta by dt square. The moment of inertia is denoted by J. So this is the diagram of the moment of inertia when ideal. Second, the torsional spring. In translational mechanical system, the spring stores potential energy. Similarly, in mechanical rotation system, torsional spring stores potential energy. Now consider the ideal elastic element, the torsional spring which is shown in the figure. The torsional spring which is shown in the figure, which has the negligible moment of inertia and friction. So when the torque is applied to the torsional spring, the torsional spring will offer an opposing torque which is proportional to the angular displacement of the body, where the T is the applied torque, K is the opposing torque due to elasticity of torsional spring, K is the torsional spring constant, theta is the angular displacement. So the opposing torque is which is proportional to angular displacement of the body is given by Tk is proportional to theta. So Tk is equal to k theta. By Newton's law, the sum of applied torque is equal to sum of opposing torque. Therefore, the T is equal to Tk is equal to k theta. So when the spring has angular displacement at both ends, the opposing torque is proportional to differential angular displacement. So that is T is equal to Tk is equal to k into theta 1 minus theta 2. And third, dashpot. Now consider an ideal frictional element which has negligible moment of inertia and that elasticity. So when the torque is applied on a dashpot, so then it is opposed by the opposing torque due to the rotational friction of the dashpot. The opposing torque is proportional to the angular velocity of the body, where T is the torque, applied torque, B is the opposing torque due to friction. So the opposing torque is given by dB is proportional to angular velocity of the body omega. So Tb is equal to B omega is equal to d theta by dt. By Newton's law, the sum of applied torque is equal to sum of opposing torque. So therefore T is equal to Tk is equal to B d theta by dt. So this is the ideal rotational dashpot with the negligible moment of inertia and the friction. Moment of inertia and the elasticity. Okay. Next, when the dashpot has the angular displacement at both ends, the opposing torque is proportional to the differential angular velocity. So therefore T is equal to dB is equal to d by dt into T1 theta 1 minus theta 2. So now we discuss the problem. Now we solve the problem. So write the equation of the motion for the mechanical rotational system shown in figure. Obtain the transfer function of the system. So the given diagram is the mechanical rotational system. So there are two moment of inertia. One is J1 and J2. So the moment of inertia has the angular displacement theta 1, and the moment of inertia of J2 has the angular displacement theta. So now we derive the transfer function of the system. So the Laplace transform of the transfer function is equal to T of s. Laplace transform of theta is equal to theta of s. Laplace transform of theta 1 is equal to theta 1 of s. So now we find out the transfer function from the given mechanical rotation system is theta of s by T of s. Okay, so now we consider the moment of inertia of J1. So the angular displacement of the mass with the moment of inertia J1 be the theta 1. So this is the free body diagram of J1 as shown in the figure. Here the opposing torques due to the moment of inertia is proportional to the angular acceleration. So Tj1 is equal to J1 T square theta 1 by Tt square. And so here what are the opposing torques acting on the J1 is Tj1 and Tk. So these are all opposing torques due to the moment of inertia and the torsional spring. So here this diagram, so the moment of inertia is connected. What are the components are connected to J1? So that is the K. Spring is connected to the J1. So when the applied torque is applied to the J1, the opposing torques due to the moment of inertia, so Tj1 and Tk. So the Tj1 and K1 marked on the moment of inertia of mass is J1. So by Newton's law, the sum of applied torque is equal to sum of opposing torque. So T is equal to Tj1 plus Tk. So now the substituting here this j1 t square theta 1 by dt square plus k into theta 1 minus theta is equal to t. So this is a differential equation of the moment of inertia of mass j1. Now taking Laplace transform of the equation 1 with a 0 initial condition. So j1 s square theta 1 of s plus k theta 1 of s minus k theta of s equal to t of s. And taking the common element t1 of s. So j1 s square plus k into theta 1 of s minus k into theta of s equal to t of s. This is the equation as 2. Next we draw the free body diagram of moment of inertia j1. So this is a free body diagram of moment of inertia j2. So here the opposing torques acting on the j2 are tj2, tk and tb. So this by Newton's law, the sum of applied torque is equal to sum of opposing torque. So when the applied torque is applied to the moment of inertia of j2, then it is opposed due to the opposed due to the moment of inertia is j1 and tk and tp. So now the differential equation of moment of inertia of mass j2 d square theta by dt square plus b d theta by dt plus k into t minus theta 1 equal to 0. So rearrange this equation, j2 d square theta by dt square plus b d theta by dt plus k d theta minus k d theta 1 is equal to 0. Now taking Laplace transform of the equation, the equation with the 0 initial condition. So we get j2 s square theta of s plus bs theta of s plus k theta of s minus k theta 1 of s equal to 0. And taking common element, so theta of s into j2 s square plus bs plus k minus k theta 1 of s equal to 0. So from the equation we find theta 1 of s. So the theta 1 of s equal to j2 s square plus bs plus k divided by k into theta of s. This is the equation number 3. Now substituting for theta 1 of s in equation number 2. So we get j1 s square plus k into j2 s square plus bs plus k divided by k theta of s minus k theta of s equal to t of s. Then cross multiply and finally we find out the transfer function theta of s by t of s is equal to k divided by j1 s square plus k into j2 s square plus bs plus k minus k square. This is a final answer for the given mechanical rotational system. So next topic, electrical analogous of mechanical rotational systems. The two systems are said to be analogous to each other if the following two conditions are satisfied. The two systems are physically different and the differential equation modeling of these two systems are same. The electrical systems and mechanical systems are two physically different systems. So this is called as the differential equation modeling of these two systems are same, then it is called as analogous system. There are two types of electrical analogous of rotational mechanical system. So that's torque voltage analogy and torque current analogy. So now let's see the analogous elements in torque voltage analogy. Now the rotational mechanical system, the torque is analogous to voltage in electrical system. The moment of inertia in rotational system analogous to inductance in electrical system. The rotational frictional coefficient in mechanical rotation system analogous to resistance in electrical system. Torsional spring constant in rotational mechanical system analogous to reciprocal of capacitance. Angular displacement in mechanical rotational system analogous to charge in electrical system. Angular velocity in mechanical rotational system analogous to current in electrical system. So next, analogous elements in torque current analogy. In the torque in mechanical rotational system analogous to current in electrical system. Moment of inertia is analogous to capacitance in electrical system. Frictional coefficient is analogous to reciprocal of resistance, and torsional spring constant is analogous to reciprocal of inductance. Angular displacement in mechanical rotational system analogous to magnetic flux, and the angular velocity in mechanical rotational system analogous to voltage in electrical system. Thank you.